Next, I want to discuss another property of functions that are related to derivatives, and that is concavity. So concavity we have, just like we had with increasing, decreasing, we have two options. A function is said to be concave up, or it has positive concavity. Those are the two ways you can say it. You can say it's concave up, or you can say it has positive concavity. In both cases, this is when the second derivative is greater than 0. What this is saying, because we know the second derivative is the derivative of the derivative, we know that the rate of change will increase. In other words, the derivative will increase as x increases. So the rate, when we say increase, we're specifically talking about becoming more positive. And I'll talk through kind of visually what this means in a second, but for now, just write those down. Concave down, just like with increasing, decreasing, concave down will be the opposite. So a function is considered to be concave down, or in other words, to have negative concavity, when the second derivative is less than 0. Did I write that properly? Yeah. Is less than 0. So the rate of change will decrease as x increases. It will become more negative. Now, from just as a quick side, from a math perspective, saying increase and decrease, totally fine here. In applied math, for example, physics, which is most of where my background is, I prefer the become more negative or become more positive, because there's places where positive and negative, where a more negative number will sometimes be described as being larger, even though technically, mathematically, it's not, because of the context and we know why we're talking about things, that gets a little bit mixed up. So that's why if you see things a little bit weird elsewhere, think about maybe more positive or more negative might be useful for you. Okay, increasing and decreasing along with concavity. So we've got a nice illustration of everything here. So we see that in this first section, the function is going down, therefore it is decreasing. Therefore, we know that the derivative has to be less than 0. Because we can visually see it decreasing, we know that the first derivative is less than 0. Same thing for this last part, which is actually why this is a typo from the textbook, and it should say decreasing. In this middle section, we can see the function is going up, so we have first derivative is positive, so it's increasing and increasing. Now, if we look at the slope at all these points, so I'm just going to sketch a couple of tangent lines as we go along, or kind of these red lines that kind of trace it. If you look during this whole first half here, you see that I have a really negative slope, a slightly less negative slope, a slightly less negative slope, 0 slope, small positive slope, slightly more positive slope. And so what we see here is this whole time the slope is becoming more and more positive over time. Initially by becoming less negative, getting closer to 0, and then becoming more and more steep in the positive direction. If you think about the numbers for this, maybe this is -4, -3, -1, 0, 1, 1.5 maybe. The opposite is true for the second half. We start with a fairly steep positive slope, less steep, 0, small negative, more negative, more negative, more negative, more negative. And that's what we mean by concavity. This is what we're talking about as we're looking at that slope. Now, the other way that people will often remember this, or that kind of a visual aid for it, is if you look in the first part, you've got kind of a smiley face, so the person is feeling positive. In the second part, you've got sort of a frowny face, so the person is feeling negative. Positive and negative concavity. Positive concavity will always form this kind of upward cup. negative concavity, the opposite, the sort of downward frown, downward cup shape. Okay, now let's talk about inflection points. So this is going to be similar but different to critical points. So just like with first derivatives, we had critical points. Second derivatives, we have inflection points. However, inflection points are only the location where concavity changes. So these will always occur at a location where the second derivative is equal to 0 or undefined. Like, those are the only places it can occur, but not every place that is a 0 or undefined second derivative will be an inflection point. So not all places where f double prime of x are equal to 0 or undefined are inflection points. So inflection points always occur where if an inflection point exists, it has to occur at a place where the second derivative is 0 or undefined. Not all places where the second derivative is 0 or undefined are inflection points. This is different than critical points, which for critical points we said everywhere that the first derivative is 0 or undefined is a critical point, but not all critical points will be a peak or a valley. In other words, a minimum or maximum. It's unfortunate that we have the two main words that become up mean different things in the different contexts. They're not perfectly analogous, but that's just unfortunately a way of the way that calculus works. Now, if you want an example of what that looks like where the second derivative is 0 or undefined without it being an inflection point, that could be something like this, where I have the function decreasing and then it goes flat for a while and then it increases. Or a function curves up and then goes flat for a while and then curves up more. Everywhere that the curve or the line is flat, there's no curvature, f double prime equals 0 or it's undefined. This whole section, the second derivative is equal to 0 because it's a straight line. But it's not a critical point because if we look this entire time outside of that, it's concave up. And then you can imagine backwards, upside down, stuff like that for alternative examples. So that's concavity and inflection points.